In today's lesson, we're going to look at connected particles again. Last time we saw connected particles, we had two particles that were separate, but they were connected by a rod, a chain, a string, a rope, and we concentrated on the forces that existed in that connector. Today we're going to look at internal forces. We're going to look at situations where one body is inside of another body. So there is no string, rope, or rod. Here's one of the most popular instances of this. So here we have a body, like a lift, and it has inside it another body, such as a box. So we can exemplify that here. In the diagram, I've got a model of a lift which has a box inside of it. So the box is a body sat on the floor of the lift, which means there is going to be a reaction force that's generated, just like if we put the box onto a table. We know that the weight of the box generates a reaction force. So anytime we have one body inside of another, we need to think about the internal reaction forces. So in this case, I've depicted two reaction forces. So because the box has some weight, it's generating a force into the floor of the lift, and in return, the floor of the lift is producing a force into the box. Both of these forces are the same. That's why I've tried to use a color code through today's lesson, so you know when forces are the same. When it comes to modeling, I can model the box inside the lift, and I can also model the box by itself. When modeling the box by itself, I'm going to consider its weight, and I'm also going to consider the reaction force acting on it. Now, if I'm considering this body, this mass by itself, let's say that it's spawned outside of the lift. We would expect it to fall towards the ground because it has mass, and due to the acceleration of gravity, that produces weight, and it should be moving down towards the ground. Without being part of the system of the lift, it would fall to the ground at a faster rate than it currently is. So there must be a resistive force, and that resistive force is one of these reaction forces. We're going to pick the reaction force that is resisting the motion of this object towards the ground. We're going to pick the reaction force that's moving up. This is the diagram that we would use when modeling just this body. And with this model, we know that we can apply Newton's second law. We can apply F equals ma to find some unknowns to solve some problems. What if there was more than just one box? What if we had two boxes? And this is often the case. A question may give you one box placed on top of another. Now, we're going to be in a similar situation. We can consider the entire system and apply Newton's second law, but we need to be aware of the internal forces that are at play. There is a reaction force in between any objects that are in contact. So, there is a reaction force between box A and box B. That's the blue force that I've drawn. And there's a reaction force between box B and the floor of the lift. That's the red force that I've drawn. Having a look at this diagram, the force that B exerts on A is exactly the same as the force A exerts on B. The force that B exerts on the floor of the lift is exactly the same as the force the floor of the lift exerts onto B. So sometimes with the wording of the question, we can find an equivalent force that we know to be the same. Once again, each of these individual masses, these individual bodies, can be modeled along with its forces. So here, if we were thinking about box A, we know that it has some weight. If it only had weight, if the only force acting on it was its weight, it would be falling towards the ground at a speed which is greater than it currently is. It's not in the lift and falling at a speed that is greater than it currently is. There is a resistive force. That is going to be the force exerted on A by B. If we are to model box B, we instantly know it has its own weight. We know it's not falling to the ground at a speed that it usually would if it was not part of this system. There is a resistive force. That resistive force is the force exerted on B by the floor of the lift. These are not the only two forces that are acting on B. We know that the reaction force, the blue force that we described as the force exerted on A by B, is going to be the same as the force exerted on B by A. So we also have this blue force here. This would be the diagram that we would use if we were modeling just the mass B. Okay, let's see this in action in an actual question. These are the diagrams that are produced. I want you to be clear on which forces are acting on each of these bodies. So here we're told a light scale pan is attached to a vertical light inextensible string. The scale pan carries two masses, A and B. The mass of A is 400 grams and the mass of B is 600 grams. A rests on top of B as shown in the diagram. The scale pan is raised vertically using the string with acceleration 0.5 meters per second squared. We're first asked to find the tension in the string. For this part of the question, we're going to go ahead and consider the whole system together. So I know there's going to be some tension in that string, and I know that the total weight is going to come from the total of the mass of the scale pan, the mass of A, and the mass of B. Now, the scale pan is a light scale pan. It has no mass. If this was a lift, we would have been told the mass and we would include that in the model. But here we have a light scale pan. The total mass of A and B is going to be 1 kilogram. So the weight is going to be 1g. We have the tension, we have the total weight, T and G. We should be able to use this to find the tension in the string. We've been told that the scale pan is going to move vertically, and we know the acceleration is 0.5. So we can set up Newton's second law, we can use F equals ma, and we're going to resolve. The resultant force is T minus G, and that's going to equal the mass of 1 multiplied by the acceleration of 0.5. In our calculator, we get an answer of 10.3. That's 10.3 newtons. Okay, so that's the tension in the string. We used the entire system as our model. In part B, we've been asked to find the force exerted on mass B by mass A. So I'm going to pick mass A for my model and think about all of the forces at play. We know that it has its own weight. That's going to be 0.4 g. And there is going to be a resistive force. The resistive force is going to be the force exerted on A by B. It's not exactly what the question has asked for, but we know that these two are going to be the same. The force exerted on B by A matches the force exerted on A by B. This unknown force we'll label as X. The particle's moving in the same direction as the entire system, and it has the same acceleration as the entire system. So we have enough information to apply Newton's second law again. The resultant force, X minus 0.4 g, is going to equal the mass here is 0.4 kilograms, is going to equal 0.4 times the acceleration of 0.5. Okay, rearranging to solve for X. And we get 4.12 newtons to three significant figures. On to part C. Now we've been asked to find the force exerted on mass B by the scale pan. We're looking for the red force in the diagram. It has a mass of 0.6 kilograms. It has a weight of 0.6 g. It has a resistive force, which we can call Y, and it also has a force that's being exerted on it by A, which we'll call X. So here's the diagram we're going to use. And once again, we're going to apply Newton's second law. F equals ma, the resultant force, Y minus X minus 0.6 g is going to equal the mass multiplied by the acceleration. We already know the value of X. We found that in part B. This is a fundamental point in all the work we do with internal forces. The force exerted by A on B is equal to the force exerted by B on A. So we know that value and we'll substitute it in. We've turned an equation with two unknowns into an equation with just one unknown. Okay, rearranging and solving for y, and we get that y, the force exerted on mass B by the scale pan, is 10.3 newtons. Okay, so just being systematic about what we're doing here. Most students don't get very far if they do not have a good diagram in front of them, and we simply had to think about the forces applicable to each of these individual masses, these individual bodies, or to the system as a whole. In each case, we were able to find an unknown force, whether it was tension or one of these internal forces. So you've heard it from me so many times. The success here comes from having a well-constructed, well-thought-through diagram from which you can apply your mathematical techniques. Okay, Halima, and we're just about finished. But before you move on to some practice questions, let's take a look at the specification and exactly what it is that students are expected to be able to show. Exactly what the examiners are anticipating you'll be confident in. While you read through, I want to quickly remind you that it will be sensible for you to come back and watch this video at a later date. Maybe come back in 2 or 3 weeks as a refresher or just before an assessment. And as you watch through the second time round, the third time round, because you've done your practice, a lot of what you go through here should resonate with you much more, and you have a chance to really embed your understanding of the difficult topics, anything that's been flagged up as A star.